Okay, thank you, Srinivas. Okay, so welcome to lecture number 31. So today we are just going to see implementation of Prim's algorithm, and yeah, we'll give a bit of introduction to dynamic programming. Before that, we'll just revise or at least take stock of the content that we have seen so far. Okay. So in the last couple of lectures, our attempt was mainly to improve implementation of this particular step. So the way we implement it is the overall algorithm itself changes a bit. I mean, in the sense that, yeah, so the detail, it's not just that you replace this with some subroutine. So like we saw yesterday with an example, with the help of an example, we are going to implement this using priority queues, which in turn are implemented using min heaps. Okay. So the idea is we store vertices in a priority queue, in fact, a min priority queue. So we just call it as queue. Okay. So each item that is a vertex has a key, which is initialized to some large value. Okay. So we call it as infinity. So each vertex also has another attribute. Okay. We call it as NB for neighbor. Okay. So a vertex, you can imagine vertex as a structure. So vertex has two attributes. So v dot key and v dot nb. Okay. So for every vertex, there are two additional attributes. Okay. So the vertex label itself is one, along with that key as well as neighbor. So the initial situation is the whole queue is filled up with these vertices, such that all vertices have equal priority, which is the largest possible priority. Let's call it as infinity. Okay, that is, it should be larger than any edge weight, a number larger than any of the edge weights. And initially, this attribute NB or neighbor is also initialized to nil. Okay, and then so what we do is to replace step 2, we essentially replace it by, we take a vertex which is obtained through extract min operation from the queue. Okay, and what we do is, so this is the vertex that is going to be added to the set of vertices that we have been constructing in this process here. Okay, S, and then v dot nb is the edge. So say v comma v dot nb is the edge that we are going to add. Okay, so that is the edge that we get. Okay, so let's go back here. Okay, so that's essentially it. Only thing is we need to update the queue, like we pointed out yesterday in yesterday's example. Okay, so how do we do update? So updation of the keys is done in the following way. So for every vertex which is a neighbor of the vertex v that we have chosen, we see if its key value is more than the weight of the edge between v and z. In that case, update z dot key to this value, and z dot neighbor now becomes v. Okay, so these are the modifications that we have. So I'll just present the full algorithm, then I'll go over the example that we did yesterday, so that we are firm with the algorithm. So yeah, so this is the full algorithm. Okay, so only difference here is we start with S as empty set. So in our earlier algorithm, we start S as singleton set, arbitrary set. I mean, arbitrary vertex. We just chose it as 1. Okay. But here we don't do that. We start with an empty tree as well as empty vertex set. Now for each vertex, we set the initialize the key to be infinity and neighbor as nil. So this is the initialization step. Now we create the priority queue by adding all these vertices. Okay, so this together we know that creation of heap takes order of n time, so we can add these in order of n time together. Now as long as queue is not empty, so we do these 4 steps. So instead of this 2 steps there, we have 4 steps here, 4 or yeah 5 steps. Okay, so take the element with the highest priority, that is the least weight. So in the first step everybody have the same priority, that is infinity. So this will be one of the vertices. Okay, this will probably depend on how you add. So if you add 1 at first, maybe you may not get 1, you'll get some other vertex, but it really does not matter. So for Prim's algorithm, it really does not matter where do you start from. Okay, which vertex you start from, the algorithm works nevertheless. Okay, so you take u to be the neighbor of v, which is in the attribute of v. Okay, now in the first step, that is first iteration, this is going to be nil, right? We have initialized v dot nb as nil for every vertex v. Okay, so for this particular vertex that we got from extracting the min element from the priority queue, or the highest priority element, this is going to be nil. Okay, so if it is not nil, we add this edge. Okay, in the first iteration, this step will not be implemented because u is nil. Okay, so in that case, what happens? You look at every neighbor of v. Okay, so for each neighbor, so initially everybody has infinity, right? So for each of them, so this is going to be true. So we w dot key is going to be larger than the weight between v and w, because we have chosen infinity as a number which is bigger than any of the edge weights. So we apply this decrease key. Okay, so w's key is decreased to weight of vw, and we set w dot nb as v. Okay, so after the first iteration, so if you look at this, so let's say the initial vertex was 1, this was the first vertex. Okay, after the first iteration, so like we saw yesterday, so the queue will look like this. Okay, so the edge weights of or the key values of 3 what are this, 3, 13, 4 and 14. Yeah, 3, 13 and 4 will be updated. Okay, according to the weights. So this is basically the weight between 1 and 3, which is 1, weight between 1 and 4, which is 2, weight between 1 and 13, which is 3, weight between 1 and 14, which is 8. Okay, so at the second iteration, so what we have is, so extract min, so what is going to come out for extract min? Okay, so I thought I corrected the typo, it is still there. Okay, I may not have compiled it. Okay, should be extract. What will be the outcome of the extract min? So the one with least key, which in other words, what is it? It is a neighbor of 1, the first vertex that we got from the queue, whose edge weight is minimum. So that is vertex, let's say u, such that which has least weight among all edges incident on the first vertex. Okay, so at the second iteration, we are going to get v as the neighbor of the first vertex whose weight is minimum among all neighbors of the first vertex. Okay, so one thing is, we need to remember that, so if we apply extract min, this vertex is removed from the queue. Okay, so this vertex no more resides in the queue, so queue will not have vertex 1 after the first iteration. So at the second iteration, I'm going to get this edge, so I'm going to extract min will result in 3, so v will be 3 here, like we demonstrated yesterday. So we'll be adding 3 to it, so our vertex set will be 1, 3 now. Okay, and u will be what? U will be 1. Okay, so we'll be adding 1 3 here, so t will be 1 3. Okay, so s will be 1 comma 3, t will be 1 edge set 1 3. Now what will happen? So now you just look at all neighbors of 3. That's exactly what this step does. Okay, all neighbors of 3 and update their weights or keys. Okay, so those neighbors which are also not neighbors of 1 will be really affected. Others will be affected. Neighbors of 1 will also be affected provided their weights are lower. Okay, so now 3 will percolate the key for 2, as well as 13 it won't change because the weight is 4 here. 1 anyway is out of the picture. 1 is not in the queue at all. So that is all it's going to. So it's going to affect the key of 2 to decrease to 2. So there will be a decrease key operation at step 2. Okay. Yeah. So one thing that I had pointed out yesterday is this heapify operation will be done after every decrease key operation. Okay. So you'll have to heapify after every decrease key so that the heap property is satisfied. Okay. I'll pause for a minute if you have any questions on the algorithm. No questions? So I hope it's all clear now. Okay. Good. So now comes to the complexity analysis. Okay. So let's measure the complexity. Okay. So now help me measuring complexity for each step or each iteration. So what is the complexity of initialization? So this is constant number of steps. I'll just write it as order 1. This updation for each vertex will be spending constant number of time because there are 2 updates. Okay, so this will be order of n. Okay, so create priority queue. We are assuming heap implementation, min heap implementation. So min heap implementation, we saw 2 lectures ago that creating the heap by adding n elements, it takes order of n time. Okay, not n log n, it takes order of n time. So this takes order of n time again. So remember that initially there are n elements in the heap. We are storing vertices, not edges. Okay. So how many iterations this while loop will run? Yeah, someone?
N minus 1.
N minus 1, it will be n because initially we have added all of them, right? So all n vertices. So though the number of edges is n minus 1, in the first iteration no edge will be added, right? So the way we have implemented, so I mean we could have started with by just taking s as 1. So this will be n iterations. Is that fine?
Yes, yes.
Yeah, n iterations. Now, yeah. So let's measure. So extract min. How much time will it take for each iteration? So
Log
find
n.
minimum order 1. Yeah, yeah. Go ahead.
Log n.
Log n, right? So for heap, removing the minimum element, that's the root, will take log n because we'll have to heapify again. Yeah, this is order of log n. In fact, theta log n. I mean, it's also lower bounded by, but I'll just write order here. Okay. So this steps just assignment, right? You're just adding this to the set. How do you implement the set? It's a matter of choice. Let's assume you have an array here. Okay. So you're adding this to the array. Or maybe just a binary vector. Okay. So 0 1 vector of length 1 to n. So if you, so v is the ith element, you set the ith element to 1. Okay. So this also I'll take as order of 1. Okay. So this again, assume that we have an implementation which can be done in order of 1 time. Okay. So now this is the part. So how much time will this take? Yeah. So, someone? It need not be tight. What do you think? I mean, even the naive bound. Let's start with the naive bound. Then we'll try to make it tighter.
Order of V.
Order of
V number of elements.
V, is it? A number of vertices. So let's take it as n. Or an order of E. Did you say E or V?
V, sir.
V. Okay. So order of V, that is order of n, right? So let's take n as a number of vertices. Order of n. Okay. So let's write in a different color. Order of n. Okay. So any other thoughts? Okay, I think
Sir,
this is
this we are doing for the 7th step, right?
yeah. Just a minute. I'll degree of v times. Okay, so that is also one good answer. Yes. So 7th and 8th combined, the whole of it. I mean, that's an iteration, right? Okay. So I forgot to mention this should be do step 8. Okay. So do step 8. So do sorry. So step 7 is a loop, right? Involving step 8. So do step 8. Yeah, so it's for steps 8, 7, and 8.
Like in the 7th step, we don't need to consider all vertices, right? Because it is like such that VW element of V. So that is
Yes.
will be the outgoing edges from V.
Yeah, so that's exactly one of yeah. So Nibedita said, right? So degree of V times. So that's exactly what you're. So
Yeah.
another approximation is order of degree of V. So let's write it there. So we'll just say degree of V because it's an undirected graph, right? So yeah, but you're right. I mean, some of it may not be even degree of V because it's only outgoing edges from that vertex, right? Which is, I mean, which is not incident on the vertices in the partial tree already. Okay, but in the worst case, it can
Hello,
be as big as degree of V. Yes.
sir. Like we are also doing heapify, so there should be a degree of V log V.
Yeah. So there is also decrease key operation. This will take order of log n time. Okay. So this will be into order of log n, right?
Okay.
Sir, but every time the number of vertices that we are choosing decreases, like V minus number of vertices in S.
Yeah. So that is also right. So this will be slightly smaller than log of 1. It will be log of I. So if or log of n minus I. That's what you're saying, right? Log of n minus I. If it is the ith iteration, there will be n minus I vertices in the heap. That's what you're saying, right? Am I right? Did I
Yes, even order of n also will become order of n minus.
okay, so you're saying this will be order of n minus I. Okay, so one, yeah. Okay, so order of n minus I into log of whatever n minus I. Okay. Yeah. So by staring at these bounds that we got, did we really gain anything? So even if you put as n minus I, okay, so up to n by 2, it's going to be bounded by n by 2, right? So even if I take it as n by 2 for n by 2 of the iterations, okay, so this is going to be like n by 2 into n by 2 times log of n by 2. It's going to be n square log n, right? Asymptotically up to a constant factor. In fact, n square by 4 into log of n by 2. Yeah. So that we didn't gain, right? So we could have used the adjacency matrix implementation, which can be even done in order of n square time together. So each iteration will take only order of n steps, merging two vertices. But there is a penalty of log n. So what did we really gain?
If we think of it in the whole algorithm, how many times this will run, I think this will run as number of times like log e will be there.
Okay, that's a good guess. So how do you reason about it?
I mean, on aggregate, if we think over the whole algorithm, it will do like that.
Okay, so but how do you argue about it?
I mean, I just had the intuition like it would.
Okay, okay. Any other thoughts?
So the order of degree v, when we add it over all the vertices, it becomes order of degree m. Sorry, order of m, because twice of all
No,
degrees.
but there is a log n factor sitting there, right? So what you're saying is, okay, order of degree v. So when you take summation, instead of just multiplying it by n, so sum of degree of v is going to be order of e. That's a good guess. There's a log n factor sitting there. That is fine. Okay, so that's a good guess. So but okay, so let's just think. I mean, that's a good reasoning also. But what is it we need to do? Say that, okay, so order of degree v sums to e. Or even the intuition by, I think it was Naveen, that order of edge times. See, all you need to do is this up. So you just account for this update operation with respect to an edge. That's the easiest reasoning. Okay. So look at, so see what is the cost list operation here? So the cost list operations here are extract min and decrease key. Okay. So let's just account for, so how many decrease key operations are performed. Okay. So let's charge. So for each decrease key, there is a responsible edge, right? There is an edge responsible for it. Yeah. So when I say decrease key W, weight of VW, so we call VW is the edge responsible for this decrease key operation. Okay. So instead of, so I'll just erase all this. So instead of counting this naively, so one reasoning is you just add up the degrees. That will also work, I think. So I'll give a slightly different way of understanding it. So what you do is, for each decrease key operation, we hold an edge responsible for it. Okay. So complexity. So counting the number of decrease key operations. decrease key. Okay, so for each decrease key, say decrease key QW weight of VW, we hold edge VW as responsible for the operation. Okay. Let's go up, yeah, to the example. Okay. So now you just look at, so the updation cost by this edge 3 2. So how many times is it going to cost the decrease key operation?
Once.
Only once, right? Why is that?
It-
So
Because one of the vertex would have been removed from which.
exactly. So that edge which causes decrease key operation, one of the endpoints is already in the tree that we have, right? It has to be in S, and hence it is not in Q. Okay, so whatever is in S is not in Q. So it's already removed from the Q. It's never going to cause decrease key operation again, right? It won't be responsible for another decrease key operation. So an edge can cause, so some of them may not even cause decrease key operation at all. Because so what will happen is, say if we had an edge between 3 and 4, right? So if I had this edge, let's say, okay, that will not cause decrease key. So edges within S may not cause any decrease key operation at all. Okay, so in the worst case, every edge can cause at most one decrease key operation. There could be scenarios where it does not cause any decrease key operation at all. So the crucial observation is every edge E can be responsible for at most one decrease key operation. So therefore, total number of decrease key operations at most number of edges, which is M. Okay, that's it. So instead of looking at the iteration by iteration, which will be basically, we'll be doing over counting. So if you look at the total number of decrease key operations which is done, which is order of E. Okay, and what is the total number of extract min operations? Order of N. Okay, so the total number of operations will be N log N. So because the time for extract min is going to be log N, similarly time for decrease key is going to be log N. You might be saying, okay, maybe it will be log of N minus I for each iteration, so it could be lesser, but it asymptotically it won't gain much. Okay, so you'll get the same bound even if you account for that. It will be like this summation, right? 1 plus etc. up to N. It's going to give us order of N square. Okay, so the overall time complexity, total time, order of, so sorry, N times time for extract min plus M times time for decrease key. This is order of n log n plus m log n. There is also additional time, which we just counted as order of n. Is there any other heavy process here? No, right? All other operations are constant time, so you can just together account for order of n. So these are all again order of n time. Okay, so plus order of n, which is subsumed by other terms. Sorry, let's write everything inside this. Okay, so this is assuming m is at least n. This will be order of m log n. Or in most of the textbook terms, this will be order of number of edges times log of number of vertices. So the idea suggested by one of you, so degree counting, right? That will also work. That's also a very good idea. Okay, so you can also use that reasoning. Okay, so every time number of operations performed is degree of v. So for each vertex, you are only counting degree of v once. Okay, so this will be bounded by sum of degrees, which is twice the number of edges. Okay, yeah. So only thing is, I mean, here that 2 factor will not come in this reasoning, because for every edge you are going to do it only once. Whereas if you count degree, I mean, it can be twice. Okay, so there will be a slight overcount, but still that is acceptable up to asymptotic.
Hello, sir.
Yes.
By the degree approach, how do we overcome the log factor?
No. So this will be, so see, each iteration, right? This will be degree of v times log n. Okay. So now if you take summation, what happens? So summation v in v degree of v times log n. So log n comes out. So this will be sum of the degrees. So this will be order of size of v times log n, right?
We have approximated log n minus I to log I for asymptotic
Yeah.
notation.
So that's not going to gain much for us in any case.
So if there was n minus I, it would have been difficult. So that's why I was asking. Okay.
Yeah, but giving a precise bound, there might be a constant gain that you gain by considering log of n minus I. In fact, it won't be really, because log of n by 2 is -1, right? So log of n by 4 is log of n minus 2. So you won't gain much at all. So the overall gain will be minus maybe something like log n, but it won't be much. Yeah. Yeah. Yeah, we have time for question. Okay, so this is certainly better than the naive implementation, particularly when number of edges is smaller than n square. Okay, but still people are not completely happy. So okay, so the question is, okay, can you still reduce this? Okay, so see, Kruskal's algorithm is also has similar complexity, right? M log n. Okay, so this is very similar to Kruskal's. So there are more sophisticated data structures. One of them is Fibonacci heap. Okay, so a different implementation of heap, which in fact allows us, so when particularly number of edges is small, in fact it allows us to shave off this log n factor. Okay, so it gives a time complexity which is like order of m plus n log n. N is anyway subsumed. Okay, I'll just briefly introduce Fibonacci without much details. I'll just tell you how it is. So what is it? Okay. Well, yeah. So this is a summary of performance of Fibonacci heaps. So Fibonacci heaps are basically another implementation of heaps. Okay. See, all of us, I mean, when we are taught heap, right? So nice thing about heaps is it's stored in an array. No linked list, no business, right? Though there is a tree structure, it's just implicitly represented by an array, right? That's a nice thing about heap. That basically makes lots of tasks much easier. You don't have to access links and so on. There is no indirect memory reference and so on. Okay. But so I think in the 1960s itself, people have found out, I think Tarian, Robert Tarian. So he found out an implementation of heap using linked lists, of course, which is amortized. It is faster. Okay, so the heap that we have seen, in the worst case, this is the time complexity. So make heap per node, it's going to be order 1. Let's ignore make heap. Okay, it's not really relevant for the binary heap. So insert operation takes order of log n, extract min takes order of log n, decrease key takes order of log n, delete takes order of log n. Okay. So let's ignore this union as well because it's not really relevant for binary heaps. Okay. So whereas Fibonacci heap, it's kind of what is called as lazy implementation. Okay. Certain updates are not done per operation. Okay. So particularly heapify and all are not really applied right away. So instead what they do is, so they maintain lots of trees. So using the link representation, the traditional trees, parent-child relationship, okay, via links. So what is gained is, if you have a large number of insert, extract, min operations or decrease key operations, okay, extract, min, it won't change much, then amortized time bound is going to be this, okay. So amortized is, so if you say, if you are taking R operations, say total time is T, so amortized time is T by R, that is per operation, okay. Individual operation, there could be something which takes order of n time, there could be something which takes order of 1. But if you average it out, it's going to be order of 1 in this case. So there is a huge gain in the cost of insertion as well as decrease key, okay. Extract min does not change, it's still the same. So yeah, insertion is not really relevant for us. So decrease key is what relevant for us, okay. So Fibonacci heap, if you do amortized, so in our case, yes, we are going to do a lot of decrease key operations, right? Order of m, okay. I'm assuming m is unbounded, n and m are unbounded, so there are lots of such operations. So in that case, amortized cost is going to be order of 1. So here, I can shave off this log n factor. We are going to apply decrease key operation the number of edges times, okay. Each of them will, on an average or amortized sense, going to cost us only order of 1 operations. So it's going to be order of n, okay. So with this, so using Fibonacci, prims can be implemented in order of n log n plus m time. Okay. So see, technically this is much better than our binary heap implementation. But many times people prefer simpler implementations. Okay, binary heap is far simpler than Fibonacci heaps. Okay, particularly analyze and understand them. So one thing is, okay, you can say, if what is the problem if somebody implements it, right? Even if the understanding the analysis or proving correctness is hard, what is the problem? So the problem is at some point, if you want to modify it, that is when our understanding of the proof comes into picture. Okay, so industry people and even academicians, when they want to implement algorithms, everybody prefers simpler implementations. Okay, even if the running time is slightly bad, people prefer that, because the reasoning is, once you have a complex algorithm or complex data structure, well, it might give asymptotically better performance, but the problem there is, if somebody wants to improve it, change, modify it to something else at some point of time, understanding is going to be really difficult. Okay, so that is why there are most of the algorithms are advocates of simple algorithms or simple implementations. Okay, so that's why in real world you'll see most of people just sticking to binary heap. They won't go for this Fibonacci heaps, though technically it is much better. Okay, so this is just an example of a Fibonacci heap. Okay, so in a Fibonacci heap, so what we do is, so instead of having just one tree, we'll have multiple trees. Okay, so there are multiple rooted trees: tree 1, tree 2, tree 3, tree 4, tree 5. Okay, so let's call this as tree 1, this is tree 2, this is tree 3, this is tree 4, this is tree 5. Okay, so in a Fibonacci heap, so we have multiple heaps. Okay, so in the implementation sense, they are all connected by linked lists. Okay, so these roots of the trees are connected by double linked lists. Okay, doubly circular linked lists. Similarly, within a heap, within a tree, all nodes at the same level are children of the same node are basically connected by a double linked list. Okay, so this is how it looks like. So the idea is you begin with, so when you say in the case of Prim's algorithm, right, you begin with n different heaps. Okay, they're all different heaps. Then what you do is, as you go on, when you do extract min or decrease key, so you try to merge them. Okay, so there is a non-trivial procedure for merging. I mean, it's not very easy to mention, but one condition is, so there is a pointer which always will point to the root which contains the least key element with the least value if you are implementing min heap. Okay, so here if you look at this pointer, this is called h min, or let's just call it as root pointer or whatever, or heap pointer. So this will point to the minimum element. Okay, so that is the property that is being maintained. But across heaps, right, you may not have this property. So each of them is an individual heap, but it might, this heap might store values which is larger than the root of this heap, and so on. Okay, so there is no interrelation. And the idea is, if you do careful update, it's something similar to, if you remember, I mean, I briefly mentioned this tree implementation of disjoint set union. There is this path compression, right? It's very similar. So what you do is, I mean, when you look for a key, when you try to extract a min and so on, you cleverly merge these trees or split the trees. Okay, either way, most of the times it's merge that happens. Okay, so what people have observed is this degree becomes an important feature. Okay, so the larger the degree, or yeah, so the larger the degree, the shallower the tree becomes. Okay, so what Tarian had proved is degree kind of stays like order of log n. So they have an implementation of each of these operation: decrease key, extract min, as well as union. So in this case, union also comes into picture, because you might also have to merge two heaps. Okay, when you implement decrease key as well as extract min, or even insert operation. Okay, so they have ensured that this degree is going to be log n. Okay, that kind of ensures that many of these operations can be done in amortized order of one time. Okay, so yeah, usually this, I think at least previous 3 instructors have taught it, so I am skipping it. Particularly, I mean, because we are in the online mode, I don't think it's worth going into that detail. Okay, because we have gone fairly slow. When I compare with the previous offerings of this course, I am at least behind 3-4 lectures. Okay, it may be also because we had 5-6 tutorials. Many of the times people hardly have tutorials. Nevertheless, so I'll be skipping the details. It's probably one of the most involved analysis in CLRS book. So those who are interested, there is a separate chapter for Fibonacci heaps. I think chapter number 17. Have a look at it. Okay, so there is a full detailed analysis. It's fairly interesting analysis, because that's kind of tells us how amortized analysis is done. What you do is you attach a potential function, then show that after every operation potential decreases. Okay, so overall the total number of operations is comparable to the potential. That is the idea. Okay, so
Sir,
yeah.
sir, why can't we do amortized on binary heaps?
So binary heaps amortized does not save you much. Okay. So we did amortized on disjoint set union, right? The analysis was essentially amortized. I didn't really advertise it as amortized because so when so what we did is the total number, right? Total number of or total number of operations that is needed to perform n union operations is so much. So then I said, okay, you divide by n to get per union operation. Okay. So that was kind of amortized analysis. For binary heap, amortized analysis really does not save much. Asymptotically, it gives the same bound as the worst case. Okay. So you do an amortized analysis only when you get a bound better than the worst case. But amortized works only when you have large number of operations. This won't work for a small number of operations. Okay. So that's a difference between amortized and worst case.
So when we have large number of operation, is amortized is equal to the average case analysis?
No. Average case is I mean, see, amortized has average, but it's average on these operations, right? When you say average case, it's on inputs, averaged over all inputs. Okay. Here, the input will be the same, right?
Yeah.
You are given the input, then you have a sequence of operations. When I say amortized, okay, so I count the total number of operations which is performed for this sequence of operations on the data structure, and I divide by the total number of operations. That is amortized. Whereas average case is something completely different. Average case is like you take average over all possible inputs. That is different. Okay.
Okay.
So yeah, amortized is usually for per operation or per task kind of. So you divide, so you basically count the total operations, divide by the total number of tasks, then you have charge for per task. So that is called amortized. It's usually relevant only when the number of tasks is huge. Okay, so unbounded. Then this makes sense.
Hello.
Yeah.
Sir, like just a bit, it confused me here that what is the difference between a task and an input here?
No. When I say task, see, I use the term operations, right? For processor operations as well as data structure operations. So I said I use the term task for the data structure operation. Say, for example, extract, min, or insert. Okay.
Okay, sir.
Because otherwise I felt confused. I mean, I used operations for two. I realized that I'm using the term operation for both. See, one operation is the processor operation, right? Say arithmetic operation or whatever. So that's basically time complexity. The other operation is for the data structure. What is operation? Make, heap, extract, min, or insert, decrease key. So I use the term task for these. That's all. Okay.
So amortized analysis is averaged over the tasks.
Yeah, the number of tasks.
The number of tasks for a particular input.
Yeah, so the input is fixed. Input is done. Okay, so there is no changing over. You're not running over all inputs and so on.
Okay.
Yeah.
So the input will be the when we do amortized, we can fix the worst case input and do amortized analysis.
You're
right?
You're right. Yeah. So it's worst case over the input.
Yeah.
It's amortized over the. I mean, like I said, if you have T or some K number of tasks, it's amortized over the number of tasks. That's all. Okay. Because what it means, like, so if you just, okay, you can imagine, okay, there is a machine which performs these tasks. Okay, I just go and press a button, okay, say decrease key. Okay. So for some arbitrary such event, there is no guarantee that the running time is order of 1 or order of log n. If you do this pressing of the button a significant number of times, then overall, if you divide by the number of times you have pressed the button, you're going to get this bound. That is what. Okay.
Yeah. So when we say for a fixed input, is it only like the algorithm is only running once?
Huh.
And in that once, per task, this amortized input gives the time complexity.
Yeah.
Like say, I guess per iteration of the task.
Yeah, I mean iteration, or say if you have an input, let's say a graph, okay, you are performing this operation, say some n times, okay. So this amortized bound, if it is t, so it basically says overall your time is going to be n times t, so that per operation that you have done or per task that you have done, your time complexity is going to be t. Okay, but it's not, if you go and measure for each individual task, it may not be. Some of them will be very high, some of them will be very low. It's basically amortized, it's like smoothening. I mean, the
So
term
this task
amortized,
can also be different.
yeah.
So okay, amortized over the tasks.
Exactly. Yeah. So
Oh,
input is fixed. So like Shira said, right? It's worst case over the input, or you said, one of you said that, right? It's again worst case over the input. So you'll be taking really bad input. Even for the bad input, amortized bound is this. That's how it is. Okay.
so the extract min in Fibonacci heap, like let us
Yeah.
take this decrease key.
Yeah.
So it is per operation of decrease key,
Yes. Yeah.
and that into m is equal to the total decrease key time complexity.
Yes. Yes. You're right.
But in the binary heap also we are saying m into log n, right?
No, extract min, but the decrease key is cheaper, right? In the Fibonacci heap.
Yes. Okay, in the decrease key only I'm saying
Yeah.
we are multiplying with m in both the cases, in binary heap and in Fibonacci heap.
Yes.
But we are saying the total is different, even though. Okay, I understood now.
Yeah. So in the case of binary heap, it will be m into log n, whereas in the Fibonacci heap, it is m into order of 1. So it's order of n. Okay. So
Okay.
okay, good. So with that, we'll stop data structures as well. So from the next lecture onwards, we'll be starting with the final theme of this course, dynamic programming. I would say also the most important, because dynamic programming is something universal. Okay, so almost every problem can be solved using dynamic programming, unlike greedy. Okay.